Hi everyone, my name is Gaspard Clerc. I'm happy today to be able to present to you my short presentation about the application of fracture mechanics to engineering design of complex structures. As you probably know, the vast majority of engineering design is based on a stress-stiffness approach. Fracture mechanic design is rarely used in engineering design, and this is partly due to the difficulty of obtaining energy release rate value and difficulty of deriving the compliance crack length equation for any arbitrary sized samples. And this is exactly what we are going to look in this short presentation, how we can use the fracture mechanic approach to design a well-known sample, and then using the same approach try to design a sample which is not so common. But first, let's discuss the advantages and disadvantages of fracture mechanics and stress stiffness approach. So for a stress stiffness approach, we have material characteristic values which are widely available. It's a simple design approach, but it's generally too conservative. And also, there is difficulty with the stress stiffness approach to deal with defects in the material and the propagation in the material, for example, crack. Here, the fracture mechanic approach is interesting because it can deal with crack propagation according to different loading conditions and so on, but its application is more complicated. We have to derive the crack growth equation, it's what we're going to see after this, and also the material values, energy release rate, are more difficult to obtain, and therefore they are also less widely available in the literature. So which kind of sample are we dealing with today? Maybe some of you know the 3ENF samples, the 3-end notched flexor sample. It's a quite well-known sample where you have here a crack, here, and it's a 3-point bending test, basically. You put some load here and the crack propagated in this direction, and then you measure how much force or how much energy you need in order for the crack to propagate. Then the second sample geometry, I give it the name for 3-point central cracked flexure samples. As you can see, it's a very similar topic. We have here the support, and the force is coming from here. But this time we have only the crack in the middle section of the sample. And with the force, the crack will propagate in this direction. Or in this direction, depending, that's random. Then let's first try to apply the fracture mechanic approach on the 3ENF sample. But first, basically, what are the main steps of fracture mechanic approach? The energy release rate is given by this Griffith formula we named, where we have P is the load, B is the width of the sample, C that's the compliance, and A that's the crack length. And as you can see this equation, we need a formula, an equation which describes the compliance depending on the crack length. And for this, what several authors use, it's a Euler binary equation with written here. We have here the flexural rigidity, W is the deflection, X is simply the X coordinate along the beam, and Q is the load. So now let's check this for the 3NF sample. As told you, we have support here, and the load is coming from here. Then we have basically three different, so we have this part where the crack is. Then we have here until the load at the middle of the sample, and we have here this part until the end of until reaching the next support. This means we have a system of three differential equations which is depicted here. This system apply for this zone, this system apply for this, and this system apply for this. This equation apply for this. If you want to see the detail, you can check this publication from Yoshia, where the solving is described in more detail. But here, due to short time, I will simply give you the solution. That's the deflection here in the middle of the beam. Okay. Then we know the deflection. With the deflection, we can use the formula for the compliance, which is simply the deflection divided by the load. This gives us this formula, for the compliance, and then we can insert this formula, derivative according to A, and insert it to obtain the energy release rate. And that's this equation. Okay, that was quite easy. Now let's see how we can use this to our new sample. As I told you again, in this time we have the support here, the load is coming from here, and we have the crack. Let's see until the middle of the sample. This means we have this time two different zones. This time and here, exactly like this. Okay. Now that we have defined these two different zones, we can write our differential equation. So for the non-cracked part, we have this equation, and for the cracked part, we have this equation. Again, we have EY, which is the flexural rigidity, X, that's X coordinate along the beam, Y is the deflection, P is the load. And please note this EI over 8 for the cracked section, that's the same factor as for the ENF sample. That's simply the reduction factor due to the cracked along the beam. This is the flexural rigidity is reduced. Yeah. And we will discuss this later in the discussions as a possible cause why there is some difficulty with applying the Euler-Bernoulli equation for this kind of sample. But now let's solve this system of equation. We obtain this equation for the deflection. Again, we can apply the formula for the compliance and insert it in the G formula, which gives us this formula for the energy release rate of the 3 CCF sample. Now let's discuss shortly the crack stability for our two samples. For the 3NF sample, we want to know if the crack will propagate in a stable manner or not. To investigate this, we have to see if the derivative of the energy release rate over an increment of the crack length is negative. This basically means that when the crack is growing, it will make some energy free, and if this amount of energy released is bigger than the amount needed to grow, then the crack will propagate immediately over the complete sample length. So that's why this value here has to be negative. If we check this for the 3NF sample, then we see that the crack should be bigger or equal of 0.7 of the semi-length of the sample. Otherwise, the crack will grow unstably, and only the fracture stiffness at the beginning of the crack propagation can be obtained. Now, if we apply the same condition for our CCF sample, then we obtain this condition that the crack should be smaller or equal as the half of the length. And that's I chose for my samples and a crack length which is smaller as this condition. Now let's compare the results between the 3NF sample and the 3 central cracked flexural sample. First, we can compare the crack propagation stability between the two types of sample. For the 3NF sample, you have this graph. Here we have the energy release rate in joule over square meter, and here the crack length. Here it shouldn't not be it's not really important now. That's 3 different kind of adhesive with whom I glued my sample. But basically what we see here is that the energy release rate is going up until a value which depends on the different adhesive, and then it propagates more the quark propagation. Here the quark is growing, and the energy is not really incrementing a lot, and this means that the propagation is stable. On the right hand, we have here another type of graphic. Here we have the force and not the fractal toughness, and here we have the deformation. So we see that the force is growing, and it reaches a maximal force here, and then suddenly it decreases until complete rupture of the sample, and that's an example of an unstable quark propagation. Now let's compare the obtained energy release rate value. For the 3 ENF samples, on average, a G value of 900 joule per square meter was measured. For the 3 CCF sample, only for an 8 of 50 milliliter was a critical energy release rate value of 900 joule per square meter measured. Theoretically, with increasing age, the needed force should decrease, but none of the tested samples with a height higher than 50 millimeter did break at the expected energy release rate force. It's what I show in this graph. Here we have the force in kilonewton, here the height of the sample, here that's 50 millimeter, and this line shows which force is needed to break a sample given its height. So we see that for 60 millimeter sample, then we need 13.2 kilonewton to reach this energy release rate of 900. But the sample I tested did not fail at a force of 70 kilonewton, and I was limited by this force by the machine I had at disposition. So this means I probably would have broken with an higher force even. So that's something I cannot explain now. Now we can shortly discuss why the results were not satisfying. The main question is, why did the application of the Griffith principle to the 3 CCF samples did not deliver satisfying results? We saw this on the quark stability criteria and also on the non-expected energy release rate value. My first idea, there is two explanations possible here. First, the friction in the middle of the section, as I mentioned earlier. For the ENF sample, we use flexural rigidity divided by 8 for the cracked region. But I'm not sure that's the case for the CCF sample, as there is probably a lot of friction due to the load which is applied in this central region and so on. So maybe another value as an 8, so something between 1 and 8 should be chosen, but which number? And probably that's something which is also not linear. It probably varies over the cracked region. The second point is that the Euler-Bernoulli equation is probably not really suited for this type of sample. Indeed, the Euler-Bernoulli equation is correct for long beam with a short long beam which are not so high. And in this case, if we consider each section, we have short section with which are quite high. So probably we have a big mistake because the Euler-Bernoulli equation doesn't consider shear deformation. So that's the point. And one option which should be investigated in the future is to use a finite element model which could simulate first the shear deformation and secondly also the friction in the middle section. So in conclusion, in this short example, I wanted to show that the basic fractal mechanics principle used to characterize 3 ENF samples cannot be directly used to design any arbitrary structures. Even for a simple geometry as a 3 CCF sample, no satisfying equation was obtained. This raises the difficulty of using fractal mechanics for engineering design of more complex realistic structures. And probably the use of a more complex modeling method such as finite element method could probably be investigated. With this, I'm at the end of this presentation, so thank you for your attention.